Good afternoon, everyone. Welcome to the weekly live sessions on the finite element method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, last all the weeks, 12 weeks, we have almost covered all the important topics of finite element analysis, starting from the basic formulations of the approximate methods and ending with higher order finite elements, and then general boundary value problems for them as well. Now, so today is going to be our extra class. So in today's extra class, we will be seeing some extra things in the finite element analysis. So this is an extra session. So stay tuned with me. I will be taking you through some interesting concepts. I hope you people will get those concepts. Okay. So in today's class, we will see isoparametric mapping concept. So today's topic is isoparametric parametric mapping concept. Okay. So what happens in isoparametric mapping concept? Why we require it? I will give you the answer to these questions in a couple of minutes. So, and the basic idea behind this isoparametric mapping concept is that the shape functions are used for transforming the whatever the physical geometry of our problem will be. It is used to transform in a parent element with simple geometry. In other sense, for example, if this is some irregular geometry of our problem. This is our problem domain, something like this. Actual, actual. We will do something, some mapping we will do, or we will do some in relations and functions chapter. Like you must be knowing about relation mapping and other things. It's same like we will do some kind of mapping such that this complex geometry is change it into some simpler geometry like this. I am drawing a geometry like this. It is changed into this. This is known as parent. Okay, actual geometry. This is parent geometry. So this is simple geometry, and for this simple geometry, we will be easily able to write shape functions using Lagrange interpolation functions. So what benefit we get from isoparametric mapping is that shape function derivation, as well as we already know that in finite element analysis we have to just integrate. Integration is one of the major things in finite element analysis, because we are integrating some functions, our differential equation multiplied by error, and then minimizing it multiple and then minimizing it using different approximation methods or Galerkin method or something, whatever we are using. There is integration always. So what happens by doing this mapping, which is known as isoparametric mapping, the derivation of our shape functions as well as integration over the parent element becomes very easy. So main advantage is that first, derivation of shape function, derivation of shape function becomes easy. And second important thing is that integration that has to be performed, because it's one of the important steps in finite element analysis. Integration also becomes less like it takes less computation time, patient time. These are the advantages. Okay, these are the advantages of this isoparametric mapping. Okay, so you people got the basic concept that it's not possible for us that every geometry or every problem that we will be solving will be having elements in square form or rectangular form, and we will be easily able to write Lagrange interpolation functions or shape functions with the help of Lagrange interpolation, Lagrange polynomial. So in order to right, shape functions for that complex geometry that is also known as actual geometry. We do a type of mapping, that is map one coordinates, that's actual coordinates, to another coordinate system, such that the geometry becomes simple. Because by taking very simple geometry, what happens that derivation of our shape functions becomes very easy, as well as after that derivation of the shape functions we have to perform integration, that also becomes very less computational time it takes for integration. So, for example, if uh, uh, it is more relevant when more relevant more relevant when we are dealing with 2D problems. We are having 2D domain, okay? So, but for time being, we will limit ourselves to 1D problems. So, for 1D problems, 1D problems. So 1D problems, this parent geometry. So for example, this actual geometry has some domain x1 less or equal to x less than x2. We have to transform this into something like parent geometry, which has the extremes at 1 minus 1. Okay, so the parent geometry has the coordinates from minus 1 less or equal to s less or equal to 1. We show it like by this notation. Okay, I hope this is clear to you. And one more important thing is, in parent element, all the nodes are placed symmetrically. And in isoparametric mapping concept, the relationship between parent element coordinates and actual physical element coordinates x is expressed using the parent element shape functions as follows. So, for example, what happens is that so these are the coordinates. For example, x of S we express as summation I running from 1 to n, ni, and it's a function of S xi. Okay, xi are actual actual coordinates, and x of S is parent coordinates, parent element coordinates, and ni are shape functions of parent element. Okay, it is the basic fund of this isoparametric mapping. That is, in isoparametric mapping, we relate the parent element coordinates with the actual coordinates with the help of shape functions of the parent element, which is given by this formula. That's x of s. um, X of s is equal to summation I running from 1 to n, and I of s xi. Okay, it's very easy. Let's see this more into this concept with the help of a example. For example, I consider a three-noded linear element. Okay, three-noded element like this. Okay, it is having some irregular nodes. It's having one node, second node, third node, and their coordinates are x1, x2, x3. They are not placed at equal distance. It is actually element. Okay. So if I want to draw a parent element for it, it will be something like this. The nodes will be placed symmetrically. So I will write here, in parent element, nodes are placed symmetrically. Okay, you note this point. Okay, So, for example, it has symmetric nodes, node 1, node 2, node 3. And we know that in parent element, the domain is -1 less or equal to s less than or equal to 1. And so we have to equally distribute. So the coordinates will be -1, 0, and 1. I hope people got this point. Okay. And let u1, u2, u3 be the nodal values. Okay. So this is a three noded quadratic element. Okay. Chord element. So let's move further. And one important thing is to note there it's x coordinate system here and it is s coordinate system here. Okay, it's important to note. And now we can write the shape functions for the parent element. Okay, shape functions for parent element. So this is parent element. Okay, this is parent. Shape functions for parallel element. We have all the things -1, 0, 1, and we have s. Okay, we can easily write shape function with the help of Lagrange interpolation function. So n of 1 will be equal to, so x1 is here -1. So it will be equal to x minus x2. That is s minus 0. That is x minus x2, x minus x3, s minus 1 divide by x1 minus x2. x1 is -1, um, x1 is -1, x1 minus 0, -1, -1. Okay, I hope you got this point. It will be 1/2 of s times s minus 1. Okay, similarly you will write, because we know that no, this is Lagrange interpolation, ni of x is simply equal to, it is simply equal to uh, x minus uh, summation I running from 1 to n, okay, x minus uh, xi, x minus, sorry, I'm writing, so n1 we wrote, no, n1 we write x minus x2, x minus x3 is simply x1 minus x2, x1 minus x3. I wrote the same thing here. Okay, is the same thing here. Okay, similarly we can write n2 to be equal to s plus 1, s minus 1 upon, here x2 is 0, minus x1 is -1 times 0 minus 1. Okay, and it will be 1 minus s square. Similarly n3 I can write s plus 1, s minus 0 upon 1 plus 1, 1 minus 0. It is equal to 1 by 2 s into s plus 1. Okay, now we have to express our x coordinate system into s coordinate system. How we can do is that, uh, so in isoparametric mapping, isoparametric mapping relationship between x and s coordinate is expressed using, it is expressed using parent element shape functions. It's very important to note here. Expressed using parent element shape functions. Okay. So how we can write is that x is equal to n1 times x1 plus n2 times x2 plus n3 times x3, where n are function of s only. So capital X will be equal to 1 by 2 s into s minus 1 times x1 plus 1 minus s square times x2, and it will be 1 half of s into s plus 1 times x3. Okay, it is clear from this equation that if s is equal to minus 1, x is equal to x1. Okay, so the mapping is correct. And if s is equal to 0, x is equal to x2. Okay, and if s is equal to 1, x is equal to x3. So our mapping is correct. So the original geometry from x1 to x3 is mapped onto a line in terms of S with nodes 1, 0, and 1. Furthermore, it is important to note that x is expressed in terms of S. So for derivation of the finite element equation, it will be more convenient if S was given in terms of x. Okay, so it will be very easy if we express s in terms of x. uh, but in general it is very difficult to get inverse of the mapping. Therefore derivatives of the form du by dx must be evaluated using chain rule as follows. Okay, so what we did is that we mapped x1 actual geometry x2 with coordinates x1 x2 x3 onto a parent element with coordinates minus 1 0 and 1 in terms of s. Okay, in terms of s, and we expressed x in terms of s. And for derivation of the finite element equations, uh, mm, we x is given in terms of s, but for derivation of the finite element equations it would be better if s was given as a function of x. Okay, so we followed x as some function g of s. Okay, we got this, but s as a function of x, or uh, we got s as g inverse of x, that is very difficult to find. Okay, it's very difficult to find. So therefore derivatives of the form du by dx must be evaluated using chain rule. Okay, so if we see here, if we compute the derivative du by dx, differentiation of the primary variable with respect to x, we can write it as du by ds by dx. Okay, ds by dx. Note from the isoparametric mapping, ds by dx cannot be calculated directly. Okay, ds by dx. Okay, we have x as a function of s. We cannot calculate. We can calculate dx by ds. Not this is easily calculated. Easily calculate. Okay, but ds by dx difficult. Okay, it is very difficult to calculate. Okay, so then first dx by ds, we first calculate dx by ds, that is called the Jacobian is calculated, and it is then inverted to get ds by dx. Are you getting my point? So we have to evaluate this differentiation. Okay, we have to evaluate this differentiation. For that, du by ds is okay, it is here. We need ds by dx. Okay, we need ds by dx. We need this. Need this. Okay, but we know that we have x as function of s, so we will be able to, if we differentiate it with respect to s, dx by ds is equal to d by ds of f of s, that is f dash of s. Okay, so it is very easy to calculate. So first we will calculate this, it is known as Jacobian. So for example, if we got it as h of x, okay, h of x. So in order to get then ds by dx, we have to just invert it. We have to find h inverse of x. We get this. This is important. Okay, required. Okay, this is what we require. Okay. So, what is important is here the need for inverting Jacobian puts restriction on when we can use the isoparametric mapping. It's very important. So, since we are inverting a function, in order to have a valid isoparametric mapping, there are some restrictions. In particular, what happens in particular if the Jacobian is zero anywhere over the domain, its inverse does not exist at that point, and the mapping does not make sense. That is important. So, for example, if dx by ds is a function, some function h of x, if h of x is equal to 0 somewhere in domain, so then h inverse of x will not be defined. So our isoparametric mapping will not be valid. So this restriction, this one condition puts a restriction on the isoparametric mapping. Okay. Thus, in isoparametric mapping, elements must be avoid situations where the Jacobian is singular. Okay, for simple cases, it is possible to explicitly state conditions which will make the mapping valid. For a quadratic element, this can be easily done as follows. So, for example, what is important is that in the one-dimensional problems, it is very easy to see where the Jacobian is zero. Where the Jacobian is zero, and we can clearly put the restrictions on the domain. But if in 2D problems, Jacobian is a matrix, and in that problems, it should not be singular. That is, determinant of the Jacobian should not be equal to zero. That is important there. Okay. So for one-dimensional problem that we considered here, one-dimensional problem that we considered here, we can easily see what is the restriction on the domain so that Jacobian is valid, okay, or the mapping is valid. So first we will calculate the Jacobian. J of x. We know that J of x is ds by dx, okay? Sorry, Jacobian is dx by ds. Dx by ds, okay? So our x is this. X is this. X is this, okay? We have to differentiate it with respect to s, okay? So when we will differentiate it with respect to s, we will get something like this. 1 by 2, 2s minus 1 times x1 plus, it will be minus times 2s x2, and it will be plus 1 by 2, 2s plus 1 times x3, okay? So we will take s common, and then it will be s times x1 plus x3 minus 1 by 2 x1 minus x3 minus 2s x2, okay? So for example, if the length of the element, actual element, if length of actual element equals 1, that is from x1 to x3, uh, it is whole equal to 1, okay? It is whole equal to 1, then obviously x3 coordinate is equal to x1 plus 1, obviously this is valid, okay? mm, so or not 1, we will put L, okay? Length of element is L. Then if we put x3 in the Jacobian, J comes out to be 2 times S times, sorry, S times 2x1 plus length of element plus L by 2 minus 2 S x2. Now for isoparametric mapping to be valid, J should be greater than 0 over the domain, okay? So for isoparametric mapping, So for isoparametric mapping, J must be greater than 0 in domain minus 1 less or equal to S less than or equal to 1. Okay, so since J is a linear function of S, it is enough to check the values of J at minus 1 and plus 1. Okay, so for that, J of minus 1 should be greater than 0. Okay, which implies that uh, minus 2x1 minus L plus L by 2 plus 2x2 should be greater than 0, or x2 should be greater than x1 plus L by 4. I hope you people are getting this point. And J of 1 should be greater than 0. Both should be greater than 0. Okay, then only we will get J not to be equal to 0. It will imply that 2x1 plus L by 2 minus 2x2 should be greater than 0. Or we will get a condition x2 minus x2 should be greater than minus x1 minus 3L by 4. Or we can write x2 should be less than x1 plus 3L by 4. So isoparametric mapping for a quadratic element is valid as long as the middle node. So our middle node is, if our middle node is placed like this, if x2 is such that x1 plus 3L by 4 value is greater than x2, and x2 is also greater than x1 plus L by 4. If this condition is met, that is, if this middle node is having this restraints, then our isoparametric mapping is valid for 1D element. Okay, I hope you people got this point. Then moving forward, we will follow some problems. Okay, so for today's session, problem one, let me take a few minutes break. So problem one for today's session is, so what we have to do is we have to write explicit expression for isoparametric mapping for a three-noded element as shown. So three-noded element is like this. It is having node 1 here, another node 2 here, and another node 3 here. It's in x coordinate system, and the nodes are located at x is equal to 1, x is equal to 2, and x equals 4. It's a three noded element, and we have to write explicit expression for isoparametric mapping. Okay, so we know that for isoparametric mapping, x of s is mapped to s coordinate system with parent element shape functions as 1 by 2 s into s minus, sorry, s into s minus 1 times x1 plus 1 by 2 s into s plus 1 x3 plus 1 minus s square x2. Here it is x1 is x2 x x3. Okay, so if we put these values, x of s comes out to be 1 by 2 s into s minus 1 times 1 plus 1 minus s square times 2 plus 1 by 2 s into s plus 1 times what is x3, 4. If we solve this, x of s comes out to be 2 plus 3 by 2 of s plus s square by 2. Okay, and now we will calculate the Jacobian. Jacobian is equal to dx by ds. Okay, Jacobian is dx by ds, so it comes out to be s plus 3 by 2. Okay, so if we see that value of j in minus 1 less or equal to s less or equal to 1, j always comes out to be greater than 0, because minus 1 if we put, it is 1.5 minus 1, it is also zero point 0.5, and if we put s equal to 0 it is 1.5, and if we put s equal to 1 it is 3 by 2, so it will be always greater than 0, so mapping is valid. Okay, I hope you people got this point. So for example, if this same example, now problem, second problem. Okay, so same problem, for example, if middle node was at some other distance. Okay, so this is x equals 1 is x equals 1.25, and it's x equals 4, it's x3, actually it's x2 is x1, it's 1 2 and 3. Now the isoparametric mapping will look like x is equal to 1 by 2 s into s minus 1 times x1 is 1 plus s square minus 1 times x2 is 1.25. Okay, plus 1 by 2 s into s plus 1 times 4. Okay, so if we solve this, x comes out to be 5 by 4 of s square plus 3 by 2 of s plus 5 by 4. So if we see, Jacobian comes out to be 5 by 2 of s plus 3 by 2. This is actually 1 by 2 5 s plus 3. So if we see that Jacobian j is equal to 0, so in minus 1 less or equal to s less than or equal to 1, j comes out to be 0, because if s is equal to minus 3 by 5, which lies between minus 1 and 1, which lies between minus 1 and 1, Jacobian comes out to be 0. So the mapping is not valid if the coordinate x is at 1.25. Okay. In fact, minus 1 less or equal to s less than 3.5. J is negative for minus 3.5, so J is positive. It can be seen from the figure. Okay. So this mapping is not valid. So I hope this was enough for this isoparametric mapping. I hope I covered all the things, whatever there were in this isoparametric mapping. So you can solve all the previous problems that were there that we solved using, I mean to say that linear elements. You can solve all those problems with quadratic elements, and you can compare how the solution accuracy has increased. So you can see how solution has increased and what is the benefit of using higher order elements. And do we actually require lesser number of higher order elements so that we have, I mean to say that we get a very good close solution to our actual solution of the problem. So if I again teach you the same thing, because the coming syllabus, it is the quadratic isoparametric element for the general one-dimensional boundary value problem. Same one-dimensional boundary value problem now, but we have to use quadratic isoparametric element formulation. I told you how to do the isoparametric formulation. You have to turn your actual geometry to parent geometry, that is the S coordinate system. And then you have to perform the integration and all the other steps that we use it to do in our one-dimensional problems, okay, with linear elements, not quadratic elements. This is there, all the things are there. You can do everything there. So if you people have any questions, you can ask. If you don't have any questions, you can leave. Thank you. Thank you for joining the session.